So now we understand that vector spaces are ecosystems in which we can add and we can multiply by scalars. And that's all we need to know. And linear transformations are functions that can respect that. They're functions which, when we take a linear combination before transformation or a linear combination after transformation, the result is the same. So now we come to the moment that we've all been waiting for, which is if I have a linear transformation on a vector space, how do I determine a matrix that completely captures the action of that linear transformation on the entirety of its domain? So what we argued for in the last video is that if I have a linear transformation from some domain X to some codomain Y, that because of linearity, because of the ability of the basis of the domain to determine the entirety of the vector space in the domain, a linear transformation, because of its ability to respect linear combination, can also be completely determined by what it does to that basis. So because the basis determines the entire vector space, the transformation's effect on that basis will determine the entire transformation. So all I need to do in order to know T, my transformation, completely, is to know what it does to E1 and to E2. So what does that look like in practice? Well, first of all, suppose that I have some vector v, arbitrary vector v, in my domain. Then because E1 and E2 is a basis for the domain, that means that there's exactly one way that I can write v as a linear combination, C1E1 plus C2E2. So what's going to happen if I transform that vector into T of v? Well, because T is a linear transformation, because it satisfies the commutation, because it doesn't matter if I do linear combination first, transformation second, or vice versa, that the image T of v is going to be C1 times the image of E1 plus C2 times the image of E2. So what that means is that I can take this linear combination, C1 times T of E1 plus C2 times T of E2, and every linear combination can be interpreted as a matrix vector product. And that's the key observation. We've made that observation before, but this is where it's really going to shine. Because if I instead interpret this linear combination, C1E1 plus C2E2, as the coordinates of a vector, we're going to call those coordinates C1 and C2, then what that does is it interprets T of v as the matrix vector product, where the vectors T of E1 and T of E2 are the columns of my matrix, and C1 and C2 are the weights in this vector over here on the right-hand side. In other words, this linear combination is nothing more than the product of the matrix whose columns are T of E1 and T of E2 by the column vector C1, C2. And this holds for any vector v that I would have chosen back here in the domain. I can express its image under this transformation as the product of this matrix, same matrix for every vector, times the vector C1, C2. So there's two morals to this story. The first moral is that as long as I can write down a basis, which is a finite set, then any linear transformation that I can apply to the vector space of which that is a basis may be expressed as matrix multiplication. This is often called the fundamental theorem of linear algebra. Just by applying this process, I can discover a matrix, A, for which that matrix times a vector x does the same thing as the linear transformation T does. So the first moral is that every linear transformation on a finite-dimensional vector space may be expressed as matrix multiplication. The second moral is that the process that we just went through to discover this fact is constructive. And what I mean by that is that it tells us how to find that matrix as well. Here the moral is that the columns of that matrix are exactly the images of the standard basis vectors. Images here mean what happens to them when I apply T. So in other words, I can find a matrix which represents this linear transformation completely just by taking T of E1 and T of E2 and making those the columns. So this particular linear transformation that we've been showing here, T of E1 becomes the vector minus 1, 1. T of E2 became the vector minus 1, 2. That's this purple vector, this green vector. And therefore, the matrix which represents this linear transformation has as its columns negative 1, 1 and negative 1, 2. So this square matrix, this 2 by 2 matrix, then represents the action of this linear transformation on the entirety of the domain. So every linear transformation on finite-dimensional vector spaces can be represented by a matrix multiplication, and the columns of that matrix are exactly the images of the standard basis vectors. Let's look at a couple more examples. Here's an example that's taken from geometry. What matrix would I have to write down which achieves the following combination of two geometric transformations of the xy plane? First of all, a 90-degree counterclockwise rotation, followed by a vertical stretch by a factor of 3. So I'm going to sketch out what I mean here. If I start with this unit square, 0, 1, 1, 0, over here, then the action of this combination of transformations should be to rotate this square by 90 degrees about the origin, and then stretch it by a factor of 3, so the end result would look something like this. Well, according to our recipe, we can find a matrix which does this, just by figuring out what this transformation does to the two standard basis vectors e1 and e2. So, what does it do to e1? e1 is the horizontal side of this square, so what's going to happen to e1? Well, if I first rotate it 90 degrees counterclockwise, it's going to rotate up to the vertical vector 0, 1. And if I then stretch that by a factor of 3, where that ends up is the vector 0, 3 along the y-axis over here. So what that means is that the horizontal side of this unit square becomes what now looks like the vertical right side of its image. What about e2? What's going to happen to 0, 1? Well, if I rotate it by 90 degrees counterclockwise, it's going to land down here at negative 1, 0 along the negative x-axis. And if I then apply a vertical stretch by a factor of 3, that vertical stretch isn't going to change the vector negative 1, 0 because it's sitting here on the x-axis, which remains in place. And so the image of that green vector is going to be the vector negative 1, 0. So now that I know what happens to the two standard basis vectors, 1, 0 becomes 0, 3, 0, 1 becomes negative 1, 0. The matrix A for this linear transformation has those image vectors as its columns. So the first column of the matrix is the image of the first standard basis vector, 0, 3. And the second column is the image of the second standard basis vector, which is negative 1, 0. So the matrix which represents T is 0, 3 in the first column, negative 1, 0 in the second column. And now, again, the power of this is that I can apply this transformation, 90-degree rotation followed by vertical stretch, to any vector in the xy plane just by multiplying that vector by this 2 by 2 matrix. So again, the recipe here to determine a matrix for any linear transformation is just determine what does it do to the standard basis vectors, and then use those images of the standard basis vectors as the columns of our matrix. We're going to conclude with an even more surprising example. So a few videos ago, we saw that we can study in linear algebra spaces of polynomial functions, because the space of quadratic polynomials, for example, is itself a vector space. So I want to close by looking at an example of a transformation on that vector space. And here's the promise I'm going to make to you, that we are going to use linear algebra to do calculus. Now, how do we get away with this? We get away with it because in calculus, the derivative is a linear operation. If you give me two functions f and g and two constants c1 and c2, then if I form a linear combination of those two functions and then take the derivative with respect to x, so we're thinking single variable calculus here, if I take the derivative, it's the same thing as if I had first taken the derivatives of f and g and then combined them using that same linear combination. These are the first rules that you learn about how the derivative works in calculus. And what that means, because the derivative is a linear transformation, it means that we can study the derivative using linear algebra. We can find a matrix that represents the derivative. And that seems pretty cool. Now, this seems surprising, but let's follow that same recipe. And the recipe was, remember, that every linear transformation can be expressed as matrix multiplication. And constructively, we can find that matrix just by finding the images of the standard basis vectors. So let's do it for the derivative as our linear transformation on the vector space of quadratic functions. So let's follow our instincts here. We start with a basis on the domain, a basis for my space of quadratic polynomials. X squared, x, and 1. Those three functions we decided form a basis for this vector space. So if I want a matrix for this transformation, I just have to find out what happens to those three basis vectors. And what we're going to get out of this is we're going to get what looks to be a 3 by 3 matrix. And the columns of those matrices are the images of these standard basis functions, if you like. Let's make that matrix. So step 1, if I want to know what the first column of my matrix is, I should apply my transformation, the derivative, to the first basis vector, x squared. So I'm really just asking, what's the derivative of x squared? And we can use calculus to remember that the derivative of x squared is 2x. Well, that's great, but I can't put 2x into my matrix as a column. What I need is coordinates for this result. I need coordinates for 2x. So what I'm really trying to do is express the result in terms of the basis that I chose. So I need to ask the question, 2x is equal to how many x squareds plus how many x's plus how many 1's? And here it's pretty straightforward to notice that I have 2 x's in my image, and I have none of the other 2. And so the coordinate vector that I'll use to represent 2x is the vector 0, 2, 0. So in coordinates, we'll call 2x 0, 2, 0. What that means then is that the first column of my matrix that represents the derivative is going to be 0, 2, 0. Because that's what happened to the first standard basis vector. The derivative of 1x squared plus 0x plus 0 times 1 is 0x squared plus 2 times x plus 0 times 1. Let's do the same thing for the other two basis vectors. What's the derivative of x? Well, the derivative of x is 1. And as a coordinate vector, that corresponds to no x squareds, no x's, and 1 times 1. So there, the coordinate vector that we get is 0, 0, 1. And that then becomes the second column of the matrix which represents the derivative. For our final basis vector, we'll take the derivative of the function 1. That's a constant function, so its derivative is 0. And 0 is the nicest vector in any vector space because its coordinates are always the same, 0, 0, 0. After all, because our basis must be a linearly independent set, the only way to represent the 0 vector in that set is with the trivial linear combination, 0, 0, 0. So the third column in my derivative matrix is the vector 0, 0, 0. So I've got now a 3 by 3 matrix that purports to be the derivative on this vector space. So if you don't believe me, let's try to actually use this matrix to find a derivative. This, I think, really illustrates why linear algebra is so powerful. We started with the derivative, which is a linear operation. And on this vector space, with this choice of basis, we discovered this matrix that hopefully represents, by matrix multiplication, what the derivative does on this vector space. To use it, let me just pick an element of this vector space. The function f of x equals negative 3x squared plus 5x minus 6. How can I use this matrix to find the derivative of that function? Well, remember, matrices operate by matrix multiplication by a vector. T of x is equal to a times x. So to find the derivative using that matrix, I need to turn this function into a coordinate vector. And I can do that just again by asking the question, how many x squareds, how many x's, and how many 1's make up this function? And that is pretty straightforward to see that it's negative 3, 5, and negative 6 respectively. So first we turn this element of my vector space into its coordinate expression as a column vector. And then we'll just multiply that column vector by my derivative matrix. And let's see what happens. When I multiply this matrix by this vector, I'll get 0 of this plus 0 of that plus 0 of that. So the first entry ends up being 0. The second entry will be 2 times negative 3 plus 0 times 5 plus 0 times negative 6. That's negative 6. And the third entry will be 0 times negative 3 plus 1 times 5 plus 0 times negative 6. That's 5. So there's the result of multiplying my derivative matrix by this coordinate vector. But what does that mean? In order to understand the meaning, we'll translate these coordinates back into an expression for this as an element of P2. As an element of P2, it's 0x squareds plus negative 6x's plus 5 1's. In other words, it's the function f of x equals negative 6x plus 5. And sure enough, that's exactly the answer that a student taking calculus would have told us is the derivative of this function. So we're now at a place where we've really unlocked Pandora's box of linear algebra. Anything which we can call a vector space, because it includes linear combination, because we can add vectors and multiply them by scalars, is a platform on which we can use linear algebra to study things. And any linear transformation we can turn into a matrix, as long as that vector space was finite dimensional, and use the properties of that matrix to do the same things that that linear transformation would have done. This is so powerful that as a first example, we can use a matrix to take a derivative of a function from calculus. We could do that because that space of functions formed a vector space, and because the derivative is a linear transformation on that vector space. This is just the tip of the iceberg. Where we're going to go for the rest of the course is to explore that iceberg a little bit more fully and really help to get a sense of how we can use linear algebra and everything we're learning here to study a whole broad spectrum of different kinds of problems drawn from different areas of mathematics and its applications.